Hello, my name is Muhammad Kuzaimi. My match number is 07DTP21F1043. Today I want to present about mold design, which is the course is DJF51092-Tool design. Firstly is introduction. Injection molding is a manufacturing process used to produce part by injection molten material. Commonly, thermoplastic into a mold is one of the most prevalent methods for mass producing plastic parts with high precision and consistency. The process involves several steps. Material is injected into a mold cavity, cooled, and then injected as a solidified product. Injection molding is widely used across various industries due to its versatility, allowing for complex shapes, type, tolerance, and efficient production of a wide range of items, from small component to larger product. Objective of the project: to learn about the defect of plastic in injection molding, to learn and increase the awareness of the product, to learn about the function of injection molding, to design or procedure a high quality molded product, and last, to learn about the types of injection mold. Compare injection mold in plastic process. First, plastic process include injection molding versus extrusion. Injection molding involves injecting molten material into a mold to create complex shape, while extrusion force soften plastic through a die to create continuous shape like pipes, tubes, and sheet. Number 2, injection molding versus blow molding. Injection molding forms solid parts by injection molten material into a mold cavity, while blow molding form allow parts by inflating a molten tube or parison inside a mold. The defect of plastic injection molding. First, short occurs when the mold cavity is not completely filled with a plastic material. It results in an incomplete or undersized part. Causes can include insufficient material, inadequate injection pressure, or improper mold design. Number 2, flash. Flash is an excess material that extrudes from the mold parting line, creating a thin, unwanted edge or flange. It is typically caused by excessive ejection pressure, mold misalignment, or one-word mold. Apply mold design in initial consideration. First, short wet. The short wet refers to the amount of plastic material that needs to be injected into the mold to create a part. It is crucial to determine the appropriate short wet to the ensure that the mold can accommodate it. This involves calculating the material volume need for each part, including any runner and gate system. Number 2, the clamping force required for the mold depends on the project area of the part and the injection pressure. It is essential to calculate and select an injection molding machine with sufficient clamping force to securely hold the mold closed during the injection and cooling stage. Number 3, molding cycle. The molding cycle time includes the time required for injection, cooling, part injection, and mold opening and closing. It is crucial to optimize the cycle time for efficiency and production rate. Factors like cooling channel design and material select can impact cycle time. Number 4, number of impression. Determine the number of cavities or impression required in the mold to meet production demand. This depends on the desired production rate and the complexity of the part. More impression can increase productivity but may require a larger machine and a higher clamping force. Number 5, position and type of fit. Decide on the location and type of the gating system. Examples: screw, runner, gate. Proper gating design is essential for even material flow, minimal waste, and preventing defects like well lines and air entrapment. Number 6, mold opening force. The force required to open the mold after cooling is critical. It should be sufficient to overcome the resistance created by the molded part sticking to the cavity surface due to shrinkage. Molds need adequate ejection system, typically using ejector pins or plates, to facilitate part removal. sketch the type of injection mold. 3-plate mold. Description: this mold design consists of three main plates: the cavity plates, the core plate, and runner plate. The runner plate separate from the other plates during the injection process, allowing of the removal of the runner system separately. Advantage: allow for the production of parts with complex shapes and with a gating system that facilitates separation of runners from the part. Disadvantage: can be more complex and costly to manufacture with the additional plate and more intricate design. 2-plate mold. This mold design comprises two main plates, the cavity plates and the core plate. The runner and gate system are typically integrated into these plates, resulting in a simpler overall design. Advantage: simplicity in design and operation, lower manufacturing costs, and better suitable for smaller, less complex parts. Disadvantage: might limit the design possible due to the integration of the runner system, potentially leading to challenge in injection and part separation. Application for 2-plate molds. First, small to medium production runs. These molds are ideal for producing smaller quantities of part where the design is relatively simple and doesn't require intricate gating or runner system. They are cost-effective for limited production need. Number 2 is simpler part design. Part with less complexity and those that do not require elaborate gating or runner system are well suited for a 2-plate mold. Product like caps, containers, and basic components often fit the criteria. Number 3, low cost consideration. When cost is a primary concern, as in the case of prototyping or short production run, 2-plate mold provide a more economical solution compared to more complex mold design. Function of mold component attached at 2-plate mold. First is cavity plate. Houses the cavity or cavities shape the final part. It includes the part geometry and is responsible for creating the actual part shape during the injection process. Number 2 is core plate. Contain the core that form the internal features of the part. It works in conjunction with the cavity plate to create the complete part shape. Number 3, gate, pins, and bushing. Ensure precise alignment and accurate closure of the mold plates, aiding in maintaining part quality and consistency. Number 4, sprue, pullant or pull pin. As in the removal of the sprue, which is the excess material left in the gate after injection. It helps separate the runner and sprue from the molded part during injection. Number 5, ejector system. Comprising ejector pin and return mechanism, it facilitates the removal of the part from the mold after solidification. The ejector pin push the part out of the mold when the plates separate. 6. Cooling channel. Embedded within the plates to facilitate uniform cooling and solidification of the molten material, reducing cycle time and preventing defects in the final part. 7. Gate. Form the connection point between the runner system and the actual part, controlling the flow of material into the cavity. Complete mold designing. First, core. The core is a part of the mold that shapes the internal features or cavity of the molten product. It creates the internal structure or negative space of the final part. When the mold flows, the core and cavity sum together to form the complete shape of product. 2 is cavity. The cavity is the part of the mold that form the external feature or the positive space of the molded product. It shapes the external surface and contours of the part. The cavity and core work together to form the complete part during molding process. Insert an additional piece of the mold that can be placed inside the core cavity or cavity to add specific feature to the final part. Insert can be used to create additional details, texture, or functional component in the molded product. Parting line. The parting line is the boundary or line where the two halves of the mold meet and spread. It's the line of separation between the core and cavity side of the mold. This line determines how the final part will be divided and where the flash. excess material might occur. Achieving a precise and well-defined parting line is crucial for the quality and appearance of the molded part. Feed system in a mold. First is sprue. Sprue, the primary channel through which molten material is injected into the mold. It is the entry point where the material is introduced from the injection molding machine. 2 is runner. Runner, these are channels that distribute the molten material from the sprue to various parts of the mold where the actual product is formed. Runners help ensure even distribution of the material throughout the mold cavity. Gate system. These are the points where the molten material enters the mold cavity from the runners. Gates control the flow of material and come in various shapes and size, impacting factors such as pressure, speed, and direction of flow. Ejector system. First is ejector pins. These are the most common component of the ejection system. They are cylindrical pins that push the molten part out of the mold cavity. Injector pins are usually mounted in the ejector plate and actuated by the injection system, often by hydraulic or mechanical mechanisms. Injector plates. These plates contain the injector pins and are mounted on the rear half of the mold. They move in synchronization with the mold opening and closing, ensuring the proper injection of the part. 3 is injector retainer. This component hold the injector pins in place and allow them to move freely during this injection process. 4 is injection actuation system. This system provides the force necessary to actuate the injection mechanism. It can be hydraulic, pneumatic, or mechanical, and is designed to move the ejector plates or pins to push the molten part out the mold cavity. Mold shrinkage, taper, and tolerance. Mold shrinkage. When materials solidify after the mold process, they can undergo dimensional change due to cooling and solidification. Mold shrinkage refers to the contraction of the material as it cools, transitioning from a molten state to a solid. Shrinkage causes finished product dimension to be slightly smaller than the mold dimension. Manufacturers account for this by designing the mold to compensate for anticipated shrinkage. Materials have different rates of shrinkage, and this factor is a critical consideration in a mold design to ensure the final product meets the design specification. Taper. Taper, often referred to as draft, is a slightly angled incorporate into the vertical walls of a mold. This design element help in the easy ejection of the finished part from the mold. The taper ensures that the part can be released from the mold without damage or sticking, as it allows for clearance during the ejection process. Without sufficient taper, the part might get lodged in the mold or could be deformed during ejection. Tolerance. Tolerances are the permissible limits or variation in the dimension of a part from the intended or normal value in the context of molding. Tolerances are crucial for meeting design specification. They determine how precise the final product dimension needs to be, influenced by factors like the material used, the molding process, and the intricacies of the part design. Tighter tolerance means the finished part must be closer to the intended dimension, which might require more precise tooling and control during the molding process. Cooling system. First is cooling channel. These are passages or channels within the mold that calculate a cooling medium, usually water, to regulate the mold temperature. These channels are strategically placed to cover areas where heat accumulation is higher or to ensure uniform cooling. 2 is temperature control units. These are devices that regulate the temperature of the cooling medium flowing through the cooling channel. Tissue control the temperature of the mold to ensure the proper solidification of the material, prevent warping or stress in the final part, and optimize cycle time. Event cooling. Ensuring uniform cooling is crucial to avoid part warping or inconsistency Designing the layout of cooling channel in the mold is a critical aspect. Properly designed cooling channel help maintain consistent temperature throughout the mold. Split side cover and side activity. First is split. The split in an injection mold refers to the physical division of the mold into two or more parts. This split allows for the removal of the finished part after the molding process is complete. Multi-parts mold typically have two halves, referred to as the core and the cavity. The split can be vertical or horizontal depending on the geometry and complexity of the part being produced. Side cover. These are components integrated into the mold to cover the side of a mold cavity or core. Side cover help create more complex shape, undercut, or detail that cannot be achieved with a straightforward tool mold. They are essential for producing parts with integrated design or features that would otherwise prevent easy injection for a two-part mold. Side action. Side action are mechanical components in the mold that enable the formation of the undercut or complex features in the part being molded. This side action moves independently of the main mold opening and closing mechanism and are used to form features that would otherwise prevent ejection from a single two-part mold. Perform a 3D design of two-plate injection mold. First, design a plastic part. For the product, I have chosen to design an Carhartt logo, which is the brand of shirt. Two-plate mold of the plastic part. For the diagram above, it shows the design of the cavity and the core of two-plate mold. In the context of an logo, the term cavity and core refer to the specific area or component within the mold used to create the logo. These terms are more commonly associated with the manufacturing process of the logo. First is cavity. In the next context of an logo mold, the cavity refer to the portion of the mold that shape the outer surface of the logo. Each cavity in the mold corresponds to one logo compartment in the final logo product. The core is the part of the mold from the inner surface of the logo. It is create the positive space necessary to shape the underside or base of the logo compartment. The core and the cavity work together to form the complete shape of the logo. The core creates the bottom and side of the logo compartment, while the cavity forms the top and outer shape. Detail a drawing of the mold, which is top and bottom. The diagram above shows the detailed drawing of the two plates that are designed. The two-plate mold, a common type of injection mold used in manufacturing, consists of two main parts, the cavity side and the core side. Here are the key features and components. The assembly of the mold. The detailed drawing shows assembly design for a two-plate mold component or part. In the context of injection molding, an assembly design of two-plate mold involves the arrangement, configuration of components both the cavity and core side to create a functional and efficient mold. The assembly design ensures proper alignment and operation of the mold during the injection molding process. Describe the sustainable element to increase tool life and awareness of the mold. Proper maintenance and cleaning. Regular maintenance and cleaning of tool and equipment help prevent wear and prolong tool life. This reduces the need for frequent replacement and the associated environmental impact of producing new tools. Optimal material selection. Choosing high quality and durable material for tools components can extend their lifespan. It also reduces waste generated from discarded tools. 3 is efficient tool design. Design tool with in mind, considering factors like material, geometry, and coating to minimize wear and maximize performance. Discussion. During the designing phase of the mold gauge doesn't appear as shown in the workpiece or product. Make sure to define the workpiece properly before sketching the mold gauge on your workpiece. 2. During the exploded view, the product doesn't explode as wanted. Make sure the parts are set to single component, not all component. Conclusion. Plastic injection molding stands as cornerstone of modern manufacturing. due to versatility, efficiency, and ability to produce high quality, precise component. Its key strength includes: first is versatility. Injection molding accommodates a wide range of shapes, size, and complexity, allowing for intricate design and details in the manufacturing part. 2 is high precision. It offers excellent repeatability and precision, ensuring consist high-quality part with tight tolerance, making it suitable for industry demanding accuracy, efficiency in high volume. It excels in mass production efficiently, creating large quantity of identical parts with minimal variation in quality and cost per unit. Material variety. A wide array of material, including various thermoplastic, can be used in injection molding, allowing for diverse properties and functionalities in the produced part. 5 is reduced post-processing. Often, parts produced through the injection molding require minimal post-processing, lowering overall production time and cost. Despite its advantage, injection molding may have limitations related to initial tooling, cost, and longer setup time, making more suitable for high volume production. Overall, its ability to create complex, high quality parts at scale make it fundamental process across numerous industries, including automotive, electronic, medical device, consumer goods, and more. That's all from me. Thank you.